Good morning, all of you. Today we'll be doing the numericals based on Van Hoos factor. For complete dissociation, if it is giving two particles or 2 moles from 1 mole, two particles from one particle, or 2 moles from 1 mole, we use I is equal to 2. If 3 particles are coming from one particle, or if 3 moles are coming from 1 mole, then we use Van Hoos factor 3. For complete association, for example, acetic acid in benzene, acetic acid in organic solvent, then for complete association, suppose a dimer is formed, two together make one. Suppose a dimer is formed, then I is equal to 2. Sorry, half. I is equal to half. If you are putting 50 molecules, afterwards, after complete association, if it is forming dimer, then means 2 molecules together make one particle. So I is equal to half. If it is partial dissociation, like acetic acid in water, so it undergoes partial dissociation. So from 1 mole, how much is dissociated? From 1 mole, suppose 0.2 moles are dissociated. From 1 mole, how much is dissociated? For example, 0.2 moles. So that 0.2 is alpha. 0.2 is alpha. So in the case of acetic acid, if alpha is the amount dissociated from 1 mole, how much is dissociated? That is called alpha. If 0.2 is dissociated, then alpha is equal to 0.2. So 1 minus alpha, that is the undissociated. And the dissociated from that side, alpha plus alpha. So total number of moles after dissociation is equal to 1 minus alpha, that is undissociated, and alpha plus alpha, that is dissociated. So 1 minus alpha plus alpha plus alpha. So 1 plus alpha whole divided by starting, that is 1 mole. Similarly, for partial association, I is equal to 1 minus alpha by 2 for benzoic acid in benzene, benzoic acid in organic solvent. Let's see the numericals. A solution containing 1.9 gram per 100 ml of KCl. KCl molar mass is given, that is 74.5 grams per mole. This question is of 2019. This is of 2019. Molar mass 74.5 gram per mole. That we know that this is the original KCl's molar mass. When you add how KCl, that is 39 plus 35.5, which is equal to 74.5. This is original. Is isotonic with, means same osmotic pressure. So here the formula applied will be of osmotic pressure. Isotonic with a solution containing a solution containing 3 3 gram per 100 ml of urea. 100 ml of urea. Urea molar mass is 60, that also we know. Urea won't dissociate, but KCl in water dissociates. So the problem is with KCl. Van Hoff factor will be applying for KCl. 60 grams per mole. Calculate the degree of dissociation. Calculate the degree of dissociation. What is degree of dissociation? Degree of dissociation is alpha. Calculate the degree of dissociation of KCl solution. So they have said degree of dissociation of KCl solution. That means it is sure that the problem is with KCl because it dissociates. Assume that both are of same temperature. Assume that both are of same temperature. Both are of same temperature. So osmotic pressure, both the solutions are having same osmotic pressure. So pi 1 is equal to pi 2. Pi 1 is equal to pi 2. Or if you are taking pi 2 is of KCl, then you can put I pi 2, I pi 2. Or first you find out the molar mass, then you can apply for, in 3 parts you can do this. In 3 parts you can do this, I'll show. Pi 1, that is NB1 upon V RT is equal to NB2 upon V RT. Now RT got cancelled, V got cancelled, that is NB1 is equal to NB2. So here I haven't considered that dissociation and all, like normal undissociated one I am doing that. Or you can put here I for KCl. That time with I you have to give KCl with I. Now I am not doing that. Now what is NB1? WB1 upon MB1 is equal to WB2 upon MB2. So WB1 1.9 1.9, this is 100 ml. 100 ml means we have the 1.9 per 100 ml. So for 1000 ml, if you are this for 1000 ml, this V, if you take 1000 ml, then it will be 19. For 100 ml, 1.9. For 1000 ml, it is 19. Here also for 1000 ml, how much? Right? For 1000 ml. So here, since V get cancelled, V get cancelled. So if it is for 1.9 in 100 ml, then it will be, for 1000 ml, it will be 19. 19 upon KCl, 19 upon KCl, then W2 for 100 ml, it is 3 grams. So 1000 ml it is 30. So here 30 divided by 60, that is a molar mass. That is a molar mass. So here, what is the molar mass of KCl? KCl molar mass is equal to, you can calculate, that is here 2. So KCl molar mass is equal to 38. KCl molar mass is equal to 38. But actual molar mass of KCl is what? 74.5. What we have got, abnormal molar mass is 38. So what is Van Hoos factor? Van Hoos factor I is equal to normal molar mass divided by abnormal molar mass, which is equal to 1.96, which is equal to 1.96. 1.96. Now, in this case, KCl, they have said degree of dissociation. For us, KCl, we have learned as an example of complete dissociation. Since they are telling that there is degree of dissociation, so you have to go for partial dissociation. You have to go for partial dissociation. For us, what we learned, KCl, what we learned, this example KCl is for complete dissociation. But they have said degree of dissociation means you have to go for partial dissociation. So that partial alpha, if there is alpha, then you have to go for partial dissociation. So for partial dissociation, what is the formula for I? I is equal to 1 plus alpha in the case of partial dissociation, because KCl dissociates in water to give, see, two particles, K plus and Cl minus. So in that case we learned 1 plus alpha, 1 plus alpha, or this 1.96, 1.96 is equal to 1 plus alpha, or alpha is equal to 0.96. So what will be the percentage? If they ask for percentage of dissociation, you simply multiply this by 100. So 96%. 96% means not 100%. We learned this example for 100%. So in this particular question, since they are asking for degree of dissociation alpha, you have to go for that alpha equation. Otherwise, if this question is not there, for us KCl is 100%, not 96%. 100% means all the molecules get dissociated. Now this can be used with the this can be used how? With the other equation also, what we learned directly, that I'll be showing you. So this I have done in 3 parts. If you want to do in single step altogether, including that I, see, that is C1RT is equal to I C2RT, including this I. Then you can calculate. So I is with what? KCl. I is with KCl. So 30 upon 60. 30 upon 60 is equal to I into 19 upon 74.2. 19 upon 74.5. 74.5. Then I you can calculate as 1.96. Same thing. Then you can use that equation, alpha is equal to I minus 1 upon n minus 1. Actually, this equation is not given in your syllabus, uh, but you learn this equation. It will be useful. So, I is 1.96 minus 1 upon 2 minus 1. So, 2 minus 1 is 1. 1.96 minus 1 is equal to 0.96. Both way it is correct. You can adopt any method for this. Next question. What is the normal molar mass of what is the normal molar mass of C6H5COOH? This is part 1. Part 2. 2 gram of benzoic acid, 2 gram of benzoic acid, 2 gram of benzoic acid. What is benzoic acid? C6H5COOH is dissolved in 25 gram of benzene. 25 gram of benzene shows a depression in freezing point equal to 1.62 Kelvin. K for benzene is K for benzene is Kf for benzene is 4.9 K kg per mole. K kg per mole. What is the percentage of association? What is the percentage of association? Percentage of What is the percentage of association of acid? Acid. If it forms dimer. Dimer means two molecules together make single particle in the solution. So this is as benzoic acid in benzene. Benzoic acid in benzene, we know it is partial association. It is partial association. Benzoic acid in benzene, partial association. So what is the normal molar mass of C6H5COOH? So when you calculate all these things, 12 into 6 plus 5 plus 12 plus 16 plus 16 plus 1. So all together you will be getting what? 122 grams per mole. This is the molar mass of benzoic acid. Now 2 gram of benzoic acid is dissolved in, so Wb is given, 25 gram of benzene, that is Wa is given, shows a depression freezing point equal to, that is delta Tf. Delta Tf. So delta Tf is equal to Kf dot m. Kf dot m. You can use I Kf dot m. IKF dot m. So I am finding out like this, then I'll be uh, separately doing that. So let's see. See, original molar mass is this thing. original molar mass is this thing. So due to this association problem, the molar mass what we are getting from here is abnormal molar mass. So I am going to find out that abnormal molar mass. So normal molar mass divided by that abnormal molar mass will give you I value. Normal molar mass divided by abnormal molar mass. So I am going to do this in three portion as in the previous case. So delta TF, from this you can find out the molar mass. Molar mass is equal to Kf. Kf for benzene is 4.9. Actually, you will be seeing 5. Normally we take it as 5, no problem. 4.9 into 2 grams divided by molar mass, but I have taken molar mass on the left hand side, so I'll be putting delta T here, that is 1.62. 1.62, then 25 upon 1000. So I have got abnormal molar mass as 241.98 grams per mole. This is what abnormal molar mass. Abnormal molar mass. Now, what is Van Hoff's factor? Van Hoff's factor I is equal to normal molar mass divided by abnormal molar mass. So normal molar mass is 122. So here 241.98 I have got, which is equal to, so after calculating I'll be getting 0.504. So I have got I value. Now, benzoic acid in benzene, dimer. So, either you can use that 1 minus alpha by 2, I is equal to, 1 minus alpha by 2, or you can use that alpha is equal to I minus 1 upon 1 by n minus 1. I minus 1 upon 1 by n minus 1. So from there you will be reaching this thing only. So I am using that top equation, that is I is equal to 1 minus alpha by 2, or you can use the down equation, alpha is equal to I minus 1 upon 1 by n minus 1. So here I is equal to what is I? I is equal to 0.504 is equal to 1 minus alpha by 2. So 1 minus alpha by 2. So alpha by 2. So alpha by 2 is equal to 1 minus 0.504, which is equal to 0.496. So alpha is equal to this into 2, that is 0.992. This is alpha. If they ask for, see what they have asked, what is the percentage of association? Once you get alpha, to find out the percentage, what you have to do to find out the percentage of dissociation, you just multiply this value by 100. So percentage is equal to 99.2 percentage. 99.2%. Suppose in the numerical you are provided with percentage, then how can you find out alpha? Divide it by 1000. If alpha is given, then you can find out the percentage by multiplying by 100. If anyway alpha value is less than 1, alpha value is always less than 1. Alpha is the portion that got dissociated or associated from 1 mole. So from 1 mole, how much gone? Maybe 0.2, 0.3, 0.6, like that. So alpha value is always less than 1. So this is the percentage of association. If it is from dimer, dimer means that 1 by n. One equation we have seen. What is that equation? That is alpha is equal to I minus 1 upon 1 by n minus 1. So dimer means this n is equal to 2. This n is equal to 2. So here if I am putting n is equal to, if I am putting n is equal to 2, that is dimer. That is 1 by 2. So 1 by 2 minus 1, this much portion, 1 by 2 minus 1, that is minus half. So I'll be replacing by minus half, minus half. And I'll be multiplying this. So minus alpha by 2 here, minus alpha by 2 here. Right, then what is I? I is equal to, so here I is equal to, I'm keeping here, I'm bringing that 1 here. So here it is 1 minus alpha by 2. So on the left hand side, it will be 1 minus alpha by 2. That is 1 minus alpha by 2. So I is equal to 1 minus alpha by 2. That only we have taken here 1 minus alpha by 2. So from that equation also you can reach to this equation. So I is equal to, see I am keeping here, this minus 1 I am taking to this side, so it will be plus 1. So that 1, then already minus alpha by 2 is here, 1 minus alpha by 2. The same equation we have already learned for this benzoic acid dissolved in benzene, means in organic solvent. Next question. 0.6 ml acetic acid. Acetic acid. Acetic acid is CH3COOH. Acetic acid example we learned in two ways, that is acetic acid in water, that is partial dissociation, acetic acid in benzene, that is a complete association. So here let's see what is the question asked. 0.6 ml acetic acid having density 1.06 gram per ml dissolved in 1 liter water, dissolved in 1 liter water, 1 liter water. So this is acetic acid in water, so it is partial dissociation. I is equal to 1 plus alpha. I is equal to 1 plus alpha. This is partial dissociation, and here what is given, direct weight of solute is not given. Here this is the solute, this is the solute, water is the solvent. WB is not given directly, instead instead volume and density is given. Volume into density. So volume and density is given. So you can find out the mass. Mass is equal to, so mass is equal to volume into density. Volume into density, that is how we'll be finding out WB. Now the depression freezing point. The depression in freezing point. The depression freezing point observed. We haven't done any numerical with this observed. Freezing point is a colligative property. So what is given here is observed colligative property. Observed. For this strength. For this strength. of acids, of the strength of acids was 0.0205 degrees Celsius. So this is the depression in freezing point. Depression in freezing point means it's a colligative property, and they have said observed. So this is the observed colligative property. So which equation you will be putting? Observed colligative property upon calculated colligative property. Calculated colligative property means using the data given, you are calculating the value of the colligative property from the data. Calculate the Van Hoff factor. Calculate the Van Hoff factor. The Van Hoff factor. Van Hoff factor is I. Degree of dissociation or association is alpha. Van Hoff factor and the dissociation constant. And the dissociation constant. And the dissociation constant. What is dissociation constant? That is Ka, equilibrium constant for this acid, that is Ka. So, here, before going to solve this numerical, I am taking a preparative class of class 11th. Before going to this numerical, what is dissociation constant? So, from last year, we learned what CH3COOH in water. In water, it is an equilibrium constant, so I am putting the reversible sign. In water, that is CH3COO minus and H plus. This we learned last year. Initially, suppose you have taken C moles. Last year we took like that only. So here 0, here 0 at equilibrium. At equilibrium. So from that, if 1 mole is taken, alpha got dissociated. If C moles are taken, then C alpha got dissociated. That also we learned last year. If one mole is taken, how much got dissociated? Alpha got dissociated. If C moles are taken, then how much got dissociated? C alpha got dissociated. So how much is remaining here? How much is remaining here? C minus C alpha. So that time here, here C alpha, C alpha. This also we learned last year. What is Ka? Ka is equal to C alpha into C alpha divided by C minus C alpha. That is C square alpha square upon C into 1 minus alpha. 1 minus alpha, and C got cancelled. So we write it as C alpha square upon 1 minus alpha. So this you have to calculate Ka. So alpha we need. C you can calculate from this equation. Alpha you need. So for alpha, let's calculate this I. Let's calculate this I. So for calculating this I, so this much portion is from class 11th. C alpha square upon 1 minus alpha. Now for calculating this I, here they have given observed colligative property. Observed colligative property divided by calculated colligative property. Calculated calculated colligative property. So observed colligative property is 0.0205 divided by calculated. So I'm going to calculate that colligative property, that is delta TF. Delta TF calculated using the data, that is 1.86 kg per mole. Then what is WB? WB is 0.6 into, that is volume into density. Density, that is 1.06, this much gram divided by, and that molar mass 60 grams per mole, 60 grams per mole into 1 liter water means 1 kg water only. 1 liter water means 1 kg water. So what all things get cancelled? The things get cancelled is kg got cancelled, gram got cancelled, mole got cancelled, and finally we have only Kelvin. So what I have got after calculation is 0.0197 Kelvin. Now I can find out I. I is equal to 0.0205 divided by the 0.0197. So I is equal to 1.041. So I have got. Now here, this is acetic acid in water. You can use that equation, that is I is equal to, that is alpha is equal to I minus 1 upon n minus 1. I minus 1 or n minus 1, or since this is acetic acid in water, you can use 1 plus alpha. I is equal to 1 plus alpha. So I am using I is equal to 1 plus alpha. So what is I? That is 1.041 is equal to 1 plus alpha, or alpha is equal to 0.041. 0.041. 0.041 alpha I have got. Now I can find out that Ka. What is Ka? Ka is equal to C alpha square. What is C? C C is the molarity. What is C? C is the molarity. Ka is equal to C alpha square upon 1 minus alpha. What is C? C, this is 1 liter of water. So you can consider, since that amount of that solute is very less, you can consider it as 1 liter solution. So C is equal to, that is WB 0.6 into 1.06 upon 60. 60 into 1 liter. 1 liter. That is C. Then alpha square, that is 0.041 square divided by 1 minus 0.041. Okay. Anyway, you will be getting the answer as 1.8 into 10 to the power minus 5. This last year many times we calculated this. This is a constant value. When you calculate, you will be getting this answer only. So 1 point, this is the dissociation constant. This is the dissociation constant. So degree of dissociation is different from dissociation constant. Degree of dissociation, normally students get mistaken. Degree of dissociation is alpha. Degree of dissociation is alpha. Dissociation constant is Ka. Dissociation constant is Ka. So take care, degree of dissociation is alpha and dissociation constant is Ka. When the question comes for when the question comes for dissociation constant, students, they find out degree of dissociation and they stop. No, you have to proceed till Ka. Thank you.